Let's explore set theory. Set theory is a branch of mathematics that deals with collections of objects. A set is simply a well-defined collection of distinct objects. By well-defined, we mean that there should be a clear rule to determine whether an object belongs to the set or not. The objects in a set are called its elements or members. For example, we could have a set of fruits, a set of even numbers, or even a set of all red-colored objects. Notice, sets can contain different types of objects. Sets can contain different types of objects. Today we'll learn about sets, one of the most fundamental concepts in mathematics. A set is simply a collection of distinct objects. These objects are called elements or members of the set. Let's look at some examples. Here's a set of fruits, apples, bananas, and oranges. Here's a set of numbers, 1, 2, and 3. And here's a set of letters, A, B, and C. Sets are usually written using curly braces. For example, our fruit set would be written as curly brace, apple, comma, banana, comma, orange, closing curly brace. There are three important properties of sets to remember. First, order doesn't matter. The set 1, 2, 3 is the same as the set 3, 2, 1. Second, duplicates don't count. The set 1, 1, 2, 2, 3, 3 is the same as the set 1, 2, 3. Third, sets can contain different types of elements, numbers, letters, words, or even other sets. Let's look at some special sets. The empty set, written as curly braces with nothing inside, or the symbol phi, contains no elements. A finite set has a countable number of elements, like our previous examples. An infinite set, like the set of all natural numbers, goes on forever. We can also describe set membership using the element of symbol, which looks like this. If X is an element of set, we write X is an element of A. If Y is not an element of set, we write Y is not an element of A. Let's summarize what we've learned about sets. They are collections of distinct objects, written using curly braces, where order doesn't matter and duplicates don't count. Sets can be empty, finite, or infinite, and can contain any type of elements. Welcome! Today, we'll learn about set operations. We'll cover union, intersection, difference, and complement of sets using clear examples. Let's start with two example sets. Set A contains the numbers 1, 2, 3, and 4. Set B contains the numbers 3, 4, 5, and 6. Let's start with the union operation. The union of two sets includes all elements that are in either set A or set B or both. Let's visualize this with a Venn diagram. The union of sets A and B contains all numbers 1, 2, 3, 4, 5, and 6. Notice that 3 and 4 appear in both sets, but we only include them once in the union. Next, let's look at intersection. The intersection of two sets includes only the elements that are in both set A and set B. In our example, only 3 and 4 appear in both sets. Now, let's look at set difference. A minus B includes all elements that are in set A but not in set B. So a minus B contains 1 and 2. Similarly, B minus A contains 5 and 6. Finally, let's discuss the complement of a set. Let's say our universal set U contains all numbers from 1 to 8. Then the complement of set A contains all elements in U that are not in set A. So A complement contains 5, 6, 7, and 8. And those are the main operations we can perform on sets. Remember, union combines all elements, intersection keeps common elements, difference shows what's unique to one set, and complement shows what's not in the set. Welcome! Today we'll learn about set operations using Venn diagrams. We'll cover union, intersection, complement, and difference operations between sets. Let's start by drawing our universal set U, which contains all elements we're considering. Within this, we'll have set A and set B. Let's start with the union operation. The union of sets A and B, written as a union B, includes all elements that are in either set A or set B or both. Next is the intersection operation. The intersection of sets A and B, written as A intersection B, includes only the elements that are in both set A and set B. Now, let's look at the complement operation. The complement of set A, written as A, includes all elements in the universal set that are not in set A. The set difference operation on minus B, written as AB or A\B, includes all elements that are in set A but not in set B. Let's solve an example problem. Set A has elements 1, 2, 3, 4, 5, and set B has elements 4, 5, 6, 7. Let's find 1, A union B2, A intersection B3, AB. Let's solve these one by one. For A union B, we include all elements from both sets. 1, 2, 3, 4, 5, 6, 7. For A intersection B, we include only elements present in both sets. 4, 5. For AB, we include elements in A that are not in B. 1, 2, 3. And that's how we use Venn diagrams to visualize and solve set operations. Remember, union combines sets, intersection finds common elements, and difference shows elements unique to one set. Hello. Today, we'll explore how set theory, particularly Venn diagrams, can help us solve word problems involving groups and categories. Set theory deals with collections of objects, called sets. When problems involve overlapping groups, like people who like apples and bananas, Venn diagrams provide a powerful visual tool. Let's quickly review some key concepts. A set is a collection of distinct items. The universal set, usually denoted by U, contains all possible elements for the problem. We draw it as a rectangle. Subsets are sets contained within the universal set, often drawn as circles. The intersection, A intersect B, represents elements common to both set A and set B. The overlap, the union A union B, includes all elements in A or B or both. The complement of A prime, includes elements in U, but not in A. Cardinality, written with vertical bars like A, means the number of elements in set A. A key formula is the principle of inclusion-exclusion. For two sets A and B, the size of their union is the size of A plus the size of B minus the size of their intersection. That is, a union B equals A plus B, A intersect B. We subtract the intersection because those elements were counted twice, once in A and once in B. Let's tackle a word problem. In a survey of 100 students about fruits they like, 60 students like apples, 50 students like bananas, and 30 students like both apples and bananas. We need to find how many like only apples, how many like only bananas, how many like at least one of these fruits, and how many like neither. Let's solve this step by step using a Venn diagram. Step 1. Define sets. A is the set of students who like apples, B is the set for bananas. The universal set, U, has 100 students. Step 2, extract numbers. We have U equals 100, A equals 60, B equals 50, and A intersect B equals 30. Step 3, draw the diagram. Step 4, fill the diagram. Always start from the innermost region, the intersection. We know 30 students like both, so we'll put 30 in the overlap. Now, the entire circle, A must have 60. Since 30 are already in the intersection, the apple's only part is 60 minus 30, which equals 30. Similarly, the entire circle B is 50. The banana's only part is 50 minus 30, which equals 20. Finally, how many are outside the circles, like neither? The total inside the circles is 30. A only plus 30, both, plus 20, B only equals 80. Since there are 100 students total, 100 minus 80 equals 20 students who like neither. Step 5. Answer the questions. Now, we can easily read the answers from our completed diagram. 1. How many like only apples? That's 30. 2. How many like only bananas? That's 20. 3. How many like at least one fruit, the union? That's 30. Apple only plus 30, both, plus 20, banana only equals 80. 4. How many like neither? That's the number outside the circles, which is 20. So, by systematically using set definitions and a Venn diagram, especially filling it from the inside out, we can clearly solve word problems involving overlapping categories. Remember these steps for your own problems.